It's a great pleasure for me to open this first session of ICAP 2016 on the connection between solid state, between condensed matter physics and AMO physics. And the first speaker is Harald Hess, who will talk about from BEC in hydrogen to microscopy in biology.
Oh, great, beautiful. Yeah, okay, that's good, thank you. Thank you, it's quite an honor to be here at the opening session of the International Conference of Atomic Physics. And for me, it's actually a bit of a homecoming since I really left the field about 30 years ago. So what I have to talk about is actually more historical and maybe formative for the field. And it was also formative for myself as a young postdoc at the time. So let me begin at a point about 10 years earlier than that, literally 40 years ago. And there was a time when people were looking at the potential between two atomic hydrogen atoms. It was well known if they're opposite spins, they form a singlet state. That's a binding state for molecular hydrogen. But if they're parallel spins, they form a triplet state with a repulsive potential. And people were beginning to look at a bit more detail at the out here at larger distances to see exactly what is the shape. What is the shape of the potential? And it turns out that there is still a shallow minimum, but it's very, very shallow, and so shallow that it does not support any bound states. In fact, if you would take this gas, it would remain a gas even to absolute zero. And so Stwally and Nossenau pointed this out in a paper in 1976. And they pointed out, furthermore, that this is an excellent candidate for Bose-Einstein condensation, so much so that they emphasized it in the paper as it is the most important experiment. So they were proposing, sorry, a little out of control here. So they're proposing to work in this phase space diagram at lower temperatures, cryogenic temperatures, and up at higher densities. And this was essentially an area where Dan Kleppner had already been working at this at room temperature, and he invented the hydrogen maser at MIT. And also at MIT, Tom Graytek was experienced at low temperature and had done a number of experiments down there. So the two connected and formed a team effort to go after this project. And the first activity in the field happened in with Joke Walraven and Ike Silvera in 1980, and they established a point way out here as the beginnings of this endeavor. And this was quickly followed by other people entering the fields, going to higher densities, repeat experiments in Amsterdam, and the densities marched up. Multiple groups joined, and people were getting closer and closer to this line of Bose-Einstein condensation in hydrogen. At MIT, the approach was to put these atoms in a trap, actually in a bottle that was lined with liquid helium, and put at low temperatures, connected to a dilution refrigerator, and inside a very strong magnetic field. And as you fill the gas, you're actually filling it with the lower two hyperfine states down here, and the gas density would rise as you would fill it up. And if you'd stop filling, you notice it would decay. But the form of the decay was not simply one that would drop to zero in some exponential or power law manner, but actually indicate that one was polarizing it into a doubly polarized state. This B state was exceptionally stable and would remain. So this meant that there's now a candidate, a doubly polarized state of hydrogen that was exceptionally stable, and it would be a candidate for Bose-Einstein condensation. So all what one needed to do was simply compress the gas, and voila, we would be there. For me, I was just graduating at a time, and this clearly was sort of an ideal postdoc challenge. And I was lucky enough to enlist with Tom and Dan at the time. And so there's the apparatus have a piston, here's a thermal sensor and a pressure sensor, here's the recording media of the time, 8-inch floppies and some chart paper. Temperature and pressure could be monitored, and then you could watch the decay after the compression. And so we executed the experiment, pressurized, and we gained about an order of magnitude closer to the Bose-Einstein transition line. And we noticed that the decay at the top was, there was some extra decay, and it seemed to be associated with a potentially n cubed term, so a 3-body decay mechanism. And that seemed to place a little barrier on going up in temperature. Well, what about going down in temperature in this direction? So there one has to consider the surfaces. The bottles had surfaces coated with liquid helium walls, and so if you drop the temperature too much, the density would go up on the walls, and the density would be high enough to induce 3-body combination on the walls. So that put a barrier down in that regime. So now it seemed to be clearly blocked. But these 3-body recombination rates, they were actually predicted. We measured them, and they matched a prediction that was done at about the same time by Kagan, Vatnius, and Shlapnikov, and they matched to a T. It's actually a remarkable calculation to think of this with all its magnetic field dependence and hyperfine state dependence can be really understood that well. And if you ever challenge the theorists in their prediction, you could try to compress really fast, the sample would explode. It's a very exothermic reaction. So what does this mean? It meant my postdoc was ruined. My life was over. And went through various phases of coming to terms with that. Anger, depression, finally acceptance. Wrote the 3-body paper, and that was that. So start thinking. Nothing else to do anyway. And so come back to this diagram. What about the upper hyperfine states over here? They can actually be confined with magnetic field. You simply put 2 north poles together and you get a field 0 in the middle. That was well known. So this means you can actually bias the walls up to a higher potential. So if we put a field on, the walls are biased up, and the actual atoms can now be trapped in the center. So this is good, but now you have a question of how to cool. Obviously, you cool by the dilution refrigerator through the walls, and the hydrogen atoms would sort of scuttle back and forth, providing thermal equilibrium. But as you take the dilution refrigerator temperature down, there would eventually be a thermal disconnect, as there would be just too few atoms which could rattle back and forth at about 40 millikelvin. But now if you take the dilution temperature further down, you find, well, the flow is going to be one way. Atoms are going to be flying out. That would provide a relatively powerful cooling thing because you remove mu b worth of energy, and that can be several times kT. So for 1 atom removed, you could move potentially 10 to 20 kT of energy. So the problem again is, well, this slows because there's just too few atoms which are going to get up and over that threshold. But you can play a trick. You simply drop the magnetic field to sustain the cooling rate. So you can keep this ratio of evaporation energy, mu b over kT, and keep that a constant where this basically will just cool and chase the temperature down and down. And so I was ecstatic when I figured this out. And it means, again, with just a modest loss of density, one can go down, potentially all the way down to absolute 0. So this is exciting. I sort of kept it to myself for a while, but eventually opened up and talked to other people. And then came the story of the 3 wise men and 3 questions. And the first one came from none other than John Bardeen, the inventor of the transistor and understanding BCS superconductivity. And he was actually the father-in-law of Tom Graytek. And he was on a visit to MIT to visit his grandchildren. And Tom brought him into the lab and had him talk to me. And I explained, this idea. And he considered it. It's very quiet. And then asked one key little questions. How quickly can the gas make these energetic atoms? So that sort of stopped me there for a second. And you see, well, okay, the cross-section, it's going to be less than a nanometer square cross-section. and you actually have to generate a lot of S-wave collisions to eventually generate the atom which has enough energy to go over that barrier with many, many kT of energy. And this has an exponential dependence on this value of eta. So my initial ambitions of trying to go in with etas of 15 or so would just be too slow. They would take hours or days to get there. So I have to sort of moderate things with that mechanism and that real-time constant in mind. Next question. Dan Kleppner came by and asked, well, what about spin flips in that nice magnetic field 0 that you have at the bottom of the trap? Well, if the atom flows through it right in the middle, it'll flip spin and it'll escape. Fortunately, that was relatively easy to take care of. You can just bias the field up and form a configuration where it's quadrupolar in one dimension and a bias field takes it up in the other dimension. And I didn't know it at the time, but I was just sort of recreating the Ioffe-Pritchard trap, which was developed independently. And finally, Tom Graytek came by and said, well, what about two-body spin relaxation? These hydrogen atoms are flying around. They can pass by each other. And the magnetic field from one passing atom can change the spin or induce a transition in the other atom, let's say from the D states into a C state. And that can then thereby escape. Turns out these rate constants are pretty well known experimentally and theoretically. We're actually measuring them at the time of the lab. And on the order of 10 to the 13 atoms per cubic centimeter, they become very noticeable. And so you finally have now a competitive mechanism with evaporation. It'll either evaporate or it'll spin flip. And if you let it spin flip, you just simply lose atoms, and you lose the opportunity to evaporate them. And you make a model of that, and you find you have to adjust the path lower. And this was disappointing again. And so next morning, think about it. Well, you really have other options. You can actually control not only the height of the trap, but you can also control the shape or the size of it. So if you change the lateral size or length size or anything like that, you can now form a path of adiabatic compression, which takes you up. And if you now continue to cool from that, you might have a second chance to get and achieve the Bose condensate. And in fact, you really have to put all of this together in a nice coherent picture, looking at the thermalization, the spin relaxation, the trap shape, et cetera, and you can calculate an optimal trajectory. And with that, I set about to build the trap. It was sort of quadrupolar in the radial direction, and it had two little pinch coils at the end. The source was out here at high field, so the low field seekers would sort of flow down to the minimum. And this was sort of an Ioffe-Pritchard trap at the time. And at the bottom end, we have the detector, which was a low-temperature hydrogen maser. So we just drop the bottom barrier here with this magnetic field, and they would escape, and we would detect this transition there. There it is. I wound those magnets myself. And we turned it on a few years later. And we established a new regime down here where we no longer had this barrier to going down to lower temperatures. And so initially we successfully trapped it, and later we successfully evaporatively cooled it down to about 3 millikelvin. But beyond that was difficult. It turned out the trap was too small. We were running out of atoms. And on top of that, the hyperfine resonance detection scheme was just simply not sensitive enough. And finally, my postdoc time was coming to an end, and so I left the project. Fortunately, another student took over, postdoc John Doyle, and he then took it to a generation 2 trap, which was much larger, and he used bolometric detection at the end to see what spills out at what potential, could make these little curves which describe the temperature, and was able to move aggressively forward down to about 100 microkelvin. But still, this wasn't enough. We're running out of atoms again. And then they opted at MIT for yet another scheme for detection, which is very ambitious, which is to go in with UV detection and use a 1s, 2s transition on hydrogen to go from here to there. And turns out this transition can be sensitive to the density, and so it would be a nice measure. And in addition, if you look at the line, there are two lines, one from counter-propagating UV photons and one from co-propagating, and you would then get two peaks associated with them. And the second peak down here would be Doppler broadened, and we'd be able to actually measure the velocity or the temperature essentially in the system. And so a generation 3 trap was developed. Here you'd shoot the laser light down from another room. This is very ambitious, reflected off of a reflecting mirror down here. And down here would be a microchannel plate for detecting the Lyman alpha line. So essentially, you would relax from the 2p transition at the appropriate time. It would generate Lyman alpha line, and that would be the signal that you would detect. So it's very sensitive. And this was also a very difficult experiment. It took a number of years to eventually make that work. Actually, 5 years passed before finally they were able to observe the signal, see the hydrogen atom. And this is also the year, of course, that Bose-Einstein occurred, and these other elements, which normally one would thought would have simply crystallized or frozen out at low temperatures based on our early understanding of it. And with that signal, improvements were further made. One was able to go up just a little bit in the density in that regime, but it still required one more step of improvement to take the evaporative cooling technique a step further. Instead of evaporating out of the end on a nozzle like this, we would just evaporate with RF technique around the whole sides. And we're able to establish good signals at the time, measure the densities, measure the temperatures, and this took us into a regime which more or less sort of skirted the Bose-Einstein line like that. Now, if you look at the line very carefully, before looking at largely the blue curve and this signal from the counter-propagating photons here, there's actually an extra signal that started to appear out here, just redshifted a tiny amount, and a peak forming in here. Now, that's actually the Bose condensate. And that was about 10 to the 9 atoms were observed at the time. So finally, one was actually able to see them up here. And if you put in the parameters, the trap shape, et cetera, it matched a Thomas Fermi description of the densities that you should sort of see in there in the signal. So finally, 22 years later, it was achieved. Now, was it easily accessible? Not really. There's a very small thermal cross-section for the hydrogen to generate the energetic atoms. But it did inspire a lot of other BE systems and work in the field over the time. And for me personally, it was actually a terrific postdoc and learning experience. And I'd like to just sort of continue down that path and show you where it led me, for better or worse. So I was lucky enough after that to join AT&T Bell Labs, a big, wonderful research institution at the time. And where do I go? There's usually a question, what do you want to do? You're given just total freedom. And it was a little bit scary. Do I evaporate more atoms? And I decided no. I really wanted to do something new. It's not a great step of creativity, but I thought, well, maybe evaporate electrons might be interesting. Can we get electrons lower than the standard temperature of electrons that are normally connected to phonons in a material? So in order to gain access to that regime, one has to go to low temperature to disconnect the electrons from the solid. Phonon-electron coupling decays at lower and lower temperatures. And I decided, well, I need to have a system where I could have tunable coupling between a source and a sink. And for better or worse, I never really performed that particular experiment, but found myself going down a path where I developed a low-temperature scanning tunneling microscope that could also do spectroscopy at the same time. Put superconductors on it and was able to image vortex states and bound states. So this was a lot of fun. Down the hallway, another colleague joined, and he was also in this field of scan-probe microscopy, trying to achieve super resolution. His name is Eric Betzik. And by making a hole, a tiny little hole, but shadowed everywhere else, if the hole is smaller than the wavelength of light, you'd actually resolve things below the diffraction limit. And that was his quest. And he was actually successful to see the first single molecules at room temperature using that technique. And these are some of the data at the time. Well, we decided a little bit later, being good friends, that maybe we should combine our platforms and go into a new direction. Can we combine the low temperature platform and his near field microscopy, spectroscopy into one system? And the sample we decided to look at is gallium arsenide quantum wells. If you shine light on them, they form electron hole pairs. The electron hole pairs will luminesce, and the spectrum of their luminescence depends on the energy states of these excitons. If it's in a slightly wider part of the quantum well, maybe 11 nanometers thick, it'll be fluorescing a little bit, or luminescing a little bit more to the red. If it's a narrow part, a little bit more to the blue, and we could try to map out and make a picture. Where are the red areas, where are the blue, what's the surface like? That was technologically of interest at the time. But if we look a little bit more closely at the spectrum, we were actually in for a surprise. We saw a lot of very sharp, tiny peaks in here. This normally would have been 2 broad peaks, but it was really made out of tiny little peaks. So what we were seeing were the components, the quantum components of an inhomogeneously broadened distribution. So essentially, we spread out the data now in X and Y by scanning it, and in wavelength in the 3rd dimension. And we found that at a particular wavelength, you would see a little like a donut ring in here, and that represents one particular quantum transition. And this was of interest. In fact, Eric was thinking that, well, maybe we have a general principle here, and we could apply this to gallium arsenide, find exactly where these states were, but that really didn't lead to much. But if you just take this in general terms and note that the data, that if you can spread out an inhomogeneously distribution in some other dimension here like this, you can then go from an optical image where you see everything at once, which is broadened by the diffraction limit, to one where you can just localize one, find the center, write it, and then do that for each individually and accumulate that, and you can get that a final image. And he proposed that method, but the times were changing. First, it wasn't really clear that that was going to be successful because there just wasn't any system where it could be used. The wavelength distribution on the standard dyes were just way too broad, nothing like the gallium arsenide quantum wells at low temperatures. So, we basically left the field. Eric was seeing the limits of the near field and its biocompatibility, and there was an emphasis to make science relevant to the company at the time. And I myself was also a little bit frustrated with the limits of low temperature scanning probe microscopy and looking, well, where can this kind of technology have some economic impact? So we both left the field. And Eric went off to work with his father's company, which happened to make machine tools that were used in the auto industry. So his ambition was to save the American auto industry from bankruptcy. I wasn't quite that ambitious, but I thought, whoops. I had some experience looking at the nano side, and I thought, well, what's really missing is one has to look at large numbers. Technology is based on large numbers, huge numbers of transistors in a chip. And so I joined up in this little company called Phase Metrics, where they have a ton of different nanometer scale measurements. The dimensions of a read-write head, the fly height, the flatness of a disk, all needed to have nanometer dimensions measured very quickly, or nanometer properties too. And so I started out with just thinking, well, how about just making an interferometer? That's a quick way of getting precise measurements. If you replace one of the arms of the interferometer with an objective, you can then image a sample and re-image everything on a CCD, and you can image it at a few different phases, like that, and as a result, produce a topographical measurement of a device of interest. So instead of going with sequential measurements, which was the standard technology, I thought, well, one should do this in a simultaneous way, and was drawn to what I knew from the telecommunications industry that, well, you can use very cheap, simple little three-way fiber couplers to do that measurement. Essentially, you send light in. These are three fibers coupled together equally. It spreads out into the three exits. One you dump, one you reflect as a reference and one you use for a measurement. These two beams come back, interfere, and produce 3 output beams, each shifted with 120 degrees phase shift. And so one could use this as a very fast, cheap way to do measurements. So we put together a little instrument. It could measure fly height, could measure deflections, had good bandwidth, high throughput, et cetera, et cetera. But there were no sales. Customers didn't really care. They were bankrupt anyway, not very interested in buying new capital equipment. So I was given the message to move on or else. And another company had also bought the phase metrics at the time, and they were also interested in high throughput, high volume measurements. And I was lucky enough to play a little with some of these instruments. This machine right here measures masks used for making semiconductor chips. You have to measure nanometer dimensions everywhere, but a throughput of gigahertz is about $40 million microscope, essentially, and got involved with some other ideas and patents and the like. But essentially, this didn't really work out for me, and I thought, well, this is not my path, and I decided to move on and chose freedom. And associated with that comes this other stuff down here. Now, the trouble is, there's this question. What do you do? And fortunately for me, Eric Betzik, who was trying to save the American auto industry from bankruptcy, failed himself, and was also looking for a question of what to do next. And so we teamed up. Actually, each of us put on a shell company. I called myself New Quest Research. That was to hide the fact that I was essentially unemployed. And Eric Betzik called himself New Millennia Research. And here we are. This is a conference trying to learn what's going on. He's walking here through the jungles, lost in Hawaii. Here I'm dwarfed by the immensity of nature around me. But still, we were trying to get back in touch, learn what was going on, what happened. One of the things which had developed over the time was the invention of green fluorescent protein. This essentially is a protein that you can encode in DNA, attach that DNA information to another DNA that describes a protein of interest, and essentially you're attaching a light bulb to it. And it was very powerful because then you could then make different proteins of a cell just light up. So here the actin protein is lighting up in blue. You can have some mitochondrial protein lighting up in pink. Something on the nucleus of another specific protein can light up in green, and et cetera. This is revolutionizing the field at the time. And Eric was trying to think, well, how can you go about making a better microscope? Normally, the mode is you have an objective in microscopy, all the light goes in, you form a spot, and try to see what comes back out. Now, he was thinking, well, how about just doing some counter-propagating beams? And you can actually form a smaller spot of interest. And sort of pointed out, well, this actually is sort of done. It's common stuff in atomic physics. You form these photonic lattices. You can trap atoms in that. Marcus Greiner did this at some time earlier. Or in lithography, you can form test patterns like that. So he was drawn to that, thought a little bit more, started playing with different forms of lattices, trying to make them a little sparse so that they could be re-imaged in a nice way. But then we're still in trouble. You could write a paper on it, but that was not going to go anywhere. So how do we get out of this? There's a saying, build your wings on the way down. Well, we hit rock bottom in Tallahassee. It's a little town in Florida. And there we met, I think, the final wise man, Mike Davidson. And we went there to meet him to see a real biologist. And he explained there were new fluorescent proteins available at the time which could be activated. Let's see if I can make this work. So if you shine blue light on it, you could change the color from green to red. So you can turn the light on and off, or you can bleach them. There's a lot of flexibility in it. So this turned out to be exactly that missing link that we had earlier. So now if you have the idea of atoms or fluorescent molecules, you're spreading them out in time. In other words, you could just photoactivate a few of them in one plane up here, find their centers, localize the middle, and then bleach them out, and then move to another set and repeat the process. So here's another demonstration of the principle. So with weak activation, there's just a small subset of labels that are activated. We find the center, write it, activate, find the center, write it, bleach it, and repeat this multiple times. So instead of getting a fuzzy distribution at the top, we can then see what we called photoactivated localization microscopy. So with that, we got excited. We knew we were onto something, and we set up shop in my living room in the summer of 2005. There's an optical table, computer center's back here, the laptop. And within a couple of months, we had the system together, made contact with people at NIH who actually had invented this photoactivatable fluorescent protein, Jennifer Lippincott-Schwartz and George Patterson. And they were kind enough to let a couple of unemployed physicists come in and set up shop in their laboratory. And so we put this together, and we're starting to image some of these structures labeled with their photoactivatable fluorescent proteins. These are lysosomes, and if you go into this activation bleach cycle, you could actually see the blinking taking place. We find the spots associated with each blinking molecule and write them down, and in the end we can form a super resolution image just like that. And so the consequence was employment again. And we're actually very lucky that Howard Hughes Medical Institute was just setting up a new laboratory, a place called Genelia Farms, just outside of Washington, D.C., and they were actually looking for people doing imaging. So where do I start? I was initially thinking of trying to take this into the third dimension. How can we get the vertical position of a molecule in these three-dimensional biological entities anyway, and decide to reharness these interferometry ideas? So here, let's see if I can get this to work, is something we called Aipom. So imagine over here, if we have a molecule in between two objectives on the opposite side, it sits here between two objectives, if I raise it or lower it, I essentially change the beam path going from one side to the other. And instead of having just a simple beam splitter in here, I have a three-way beam splitter trying to emulate the single mode experiments or technology from earlier, and can project an image into that. And so at each point we measure three phases, 1, 2, 3, and the ratio of these then tells us the position to nanometer resolution. So we call this the Aipom, and this takes us from the technology there, which was a standard confocal image, has this point spread function. With the Aipom, we can get down to this lentil-shaped point spread function, which is well over an order of magnitude smaller. And then we sort of run a few experiments. This is yeast, which is budding. A particular protein called septin can form a little pinch-off structure. Or over here, focal adhesions. These are just a jumble of different proteins. You can label them one at a time, find out which head is down, which head is up. We can even measure the orientation of molecules, and we can sort of reconstruct models of how these adhesion structures work. There's a lot of regulatory and tension forces, and actually it's very important for propagating cells, cancer, and other things like that to understand these focal adhesion structures. Or even for AIDS, we're able to apply this. There is one particular protein which is associated with the pinch-off structure of the AIDS virus, and it wasn't known, does this operate from the outside on the membrane, or does it operate from inside the capsid just as it's budding out? We take images with this and conclude that, yes, it looks like it's operating from the inside. So what about Eric? We left him last with the lattice microscopy, and he started thinking about that, but actually he went off into a different direction. His ambition was to try and look at live cell imaging, and a good technique for that is to use light sheet illumination. Essentially, you want to illuminate across the sample instead of down the imaging objective. That really uses the photons most effectively for the imaging, with minimal photo damage and phototoxicity that really is important. And you decide to make this beam a Bessel beam. So if you illuminate a circle, in the back focal plane of the objective, you come out with a very long, thin, pencil-like beam, which is extended, great for getting an extended two-dimensional image. And he added on, trying to make multiple of these Bessel beams to sort of speed up the throughput. And then he got interrupted by this, got a Nobel Prize, and here he is with Princess Victoria at a ceremony on the subject of single molecule imaging in the palm microscope. And, but his heart really wasn't there. He was thinking about lattice microscopy. So if we further modify the back focal plane and change the structure, you can actually form a lattice in 2D space and make that as fine as possible illumination, and applied this to a number of examples. This is sort of the nice thing is the phototoxicity was so low, you can actually watch biological systems in time, in 3D, and without them sort of dying from the intense illumination. So this is essentially very good, pristine 4D illumination. So that was Eric's. I went off to the dark side. He was working with photons. I thought, well, maybe you can get more global context and better resolution by going off into electron microscopes. But of course, your sample is not live. You can't do continuous imaging and see the dynamics of the things, but you do get the better resolution. Everything's a trade-off here. And I was drawn to a particular challenge, which was to see the full neural circuitry of a simple brain, let's say that of a fly brain. And if you look at the size, it's about 0.5 millimeter or 1/3 of a millimeter. And in order to see the detailed circuits, you'll see in a second, you have to sample it at about 8 nanometer resolution. Now that is truly a lot of data. If you acquire the full fly brain, even for a tiny fly brain, you're talking about 100 teravoxels. And if you sample at a megahertz, that's about 3 years of data acquisition. So these are huge data acquisition projects. But also they're like a major machine vision challenge to try to process this data. And this drew a little bit, I was comfortable with it just because before I thought, well, these kind of high throughput instrumentation have a lot of potential for science too, not just technology. And I decided to use a rather unusual approach, which is a focused ion beam sectioning. So basically, you can go and let me get that under control here. You can first image the surface with a scanning electron microscope, and then polish away with the ion beam, image the surface, polish, image, polish, repeat that thousands of times, and eventually build up a 3D volume. Now, the problem is, FibSim was thought to be irrelevant because it cannot require such big volumes. And that was actually true. Here's a fly brain. And here's a typical volume that was able to be acquired with the FibSim at the time. And so what we did was just rather simple engineering here and trying to address the problems. These machines, they have frequent interrupts. You have to reheat them, and when you restart, you lose focus, you lose materials. The imaging is not continuous. You have to be sensitive to environment, to temperature. So there are a lot of things just from the toolkit of being a good physicist, good experimental physicist, you're comfortable going at it. And we combined two different companies, FEI with their focused ion beam column and Zeiss with their SEM column, and we called the hybrid a FEIS machine. And in addition, here's one of the techniques. We tried to do feedback on the ion beam, so make sure it doesn't go too high or too low or cause any damage that would be otherwise just totally catastrophic, and we couldn't recover from it if we spend a long time milling and then have a bad step. And so that allowed us to go from that small volume to a larger volume. We can zoom in. These are like 3 parts of a neuropil associated with the optic lobe. Here we see the medulla, the lobula, and the lobula plate. When you see this sort of move in time, we're moving in Z. So time is really Z dimension. This is a 3-dimensional data set. And so this took 100 days. It was about 150 microns across in size. And I'm going to zoom in about 10x. And you see this is called a chiasm in the middle. So there's a lot of circuitry that's just sort of weaving and braiding back and forth, trying to go from one module to the other module. And if you look carefully here, you can also see columns associated with the individual retina, the individual obnutidia of the fly. And here you see a big cell nucleus in there. The dark things are the mitochondria. Let me see if I can just sort of stop it here. Yes. And if you see further little dark spots right here and here and here, right there, those are synapses. They're called T-bars. That's the actual on-off switch of the fly brain. And this, of course, the next step is processing the data. There's an independent team at Janelia involved in exactly that particular thing, processing it, trying to find circuitry of interest. Now, there's one limitation. We're just able to go only about 100 microns in depth. The milling becomes unstable if you go longer than that. So we developed a technique of hot knife, where you just section it into about 30-odd sections, laminate it into little tabs, distribute it around multiple machines. So now we're in a situation where we should be able to see a fly brain in about a couple of years with several of these machines running. And we're actually doing this at the moment. Fly brains chopped up. Here's a part called, 4 tabs have been imaged. We're trying to get at this part. It's called the central complex. This is where the fly has its sense of orientation and knows where it is in the world. And people are doing research on that. And here's just a few cross-sections of that data. This is the X-ray over here, and you can see the different parts. Zooming in a little bit, you just see just amazing intricate processes going on in this poor little fly brain. Zoom in a little bit more. This right here is the cut that we did with a hot knife, and it's of good enough quality that we can actually trace right across it. So now, a final story is that this kind of long-term imaging opens up a new chance for higher resolution. Before, we're operating the microscope with a larger numerical aperture. We wanted throughput, get a lot of volume, get the full circuitry. But if you drop the numerical aperture, you get rid of a lot of spherical aberration in the electron microscope, and you can have a different operation regime down here. But because now we have the capability to run for a long time, we can actually harness this in a new way. So before, this is a chart of volume versus resolution, better resolution going down. Before we were operating up here, now we can go maybe access some cell biology down in this regime in a way that no other technique can. This is not the best resolution, but this can get volumes that other techniques cannot. Here, for example, this shows the improvement in resolution between before and after. I'll just focus on a couple simple little processes. This is a flagella on Chlamydomonas. It's an algae, and over here I'll just show a crop out of this particular image. So here there's flagella, so just watch it here. The 4 little microtubules shoot out. You saw a little micromotor in the middle, and you'll get another pass at it. You just watch this little spoke-like structure in here. It's pretty amazing. Now, if we go over here, this is a nucleus. If we just crop out the outer part of the nucleus itself, notice there's some little white dots on the outside. Those turn out to be polyribosomes. They look like little necklaces decorating the surface of the nuclei. In the middle, you might see nuclear pores. And now the difference is, instead of just seeing this in a few sections of an EM, you can see it in its entirety. So just summarizing up, I think this is nice, but we're still in relative darkness comparing to the problems in biology. In fluorescence microscopy, we're just imaging just 2 or 3 out of potentially 10,000 different proteins which are active in the cell. And there's still a lot of room for improvement. And we're actually looking at now, what is the photophysics that dies at cryogenic temperatures? And we really have to go back to the basic principles, triplet states, what's going on in the transition to understand that. We clearly need better imaging, EM imaging, and maybe combine it someday with the fluorescence imaging. And there are a lot of fun problems to go after. You can imagine, can we just see the complete DNA in the nucleus in its entirety, not spread out on the cover glass, but in its native environment? Can we see memory? Can we see what synapses formed when a fly learned to avoid a certain odor or not? And that's all in process. But I think this is all built on an experimentalist physics toolkit, which for me certainly led back to, came from the atomic physics background. And so with that, I'd like to acknowledge a number of people throughout, Eric Betzik, in particular Tom Greatek and Dan Klepner, who got me started down this path. And so if I have a final word, which I'd like to say, is just embrace the challenge when you encounter the dark side. Thanks for your attention. Okay, thank you.
So we have time for one or two questions. Yes.
Oh gosh, I'm probably at pains to say too much more about it. Let's see if I can get it. This one right here, if I can get it to go. Maybe I can just sort of stop it at a few points here. That's a side view, right there. This up here, there's several. It's part associated with the flagella, which basically drive it. And up in here, there are a series of proteins which are work on some phosphorylation cycle to sort of induce the rotation on the whole thing. This consists of about, I think, 9 microtubule pairs. There's a lot of transport going up these tubes to sort of form and lengthen them. The base is very unusual. I don't know if there's you sort of notice this little, almost a spiral structure here. Let me go a little further here. Whoop, just past it. I think you might have caught that. These are essentially little derived also from the centrosomes, which are associated with cell division, but here they're sort of re-employed to form the cilia. And you actually see daughter cilia in the same thing. I'd say right now we got the data, biologists have looked at it, and are basically trying to sort of put a story around it. And put that in context. But I think a lot of this might have been known before. You can always sort of cut through, see some of these things with even higher resolution using TEM. But here we can see the whole thing in its entirety, see the whole base structure. I think you might have seen there was a whole anchoring system down here which sort of keeps the thing from falling apart. Let's sort of move it one more time. It doesn't want to start on me. There we go. And you see all these little other things sort of spraying out and just making sure it stays stable. So I think biology is partially observational. You go in there, you see what you can sort of find, and try to put a story around it. So I'm afraid I can't sort of answer any detailed questions yet on that, other than saying, gosh, it looks cool.
I'm afraid our time is up for this talk, but I'd like to thank Dr. Hess again for a fascinating talk and some beautiful pictures. The next speaker is John Saunders from Royal Holloway, University of London, and he's going to talk about helium films at ultra-low temperatures.